So we left off talking about the common ion effect and how when we have aspects in common on both sides of an equilibrium, usually some sort of shared ion, there can be a consequence on behavior. It sort of has a tendency to moderate the behavior of the equilibrium, locking us into a certain amount of control. If we have a weak acid, we can express the equilibrium with our typical weak acid statement, where this is the undissociated acid form, and this would represent the conjugate base. Form of the acid. And in our example from the previous topic, we had pegged out the concentration of the acid and base, and we find that that sort of isolates the hydronium ion concentration, because these would then become fixed values. Now, we can use this weak acid assumption that the amount of undissociated acid and the amount of conjugate base, the amount of conversion between those is very small in the absence of any sort of external acid, basically making them constant. So this is sort of the hallmark of buffer systems, systems that contain both significant amounts of an acid, a weak acid that is, and its conjugate base. When you have significant amounts of its weak acid and its conjugate base, the systems are resistant to change in the hydronium ion concentration. Because what happens is, if you add H3O plus via the form of external acid, this reaction is driven this way. The H3O plus is consumed, the conjugate base is consumed, and the weak acid is consumed. But then we reattain equilibrium, and it reforms the amount of H3O plus. And what we find is that while the H3O plus changes, it doesn't change significantly. So this is one of the hallmarks of a buffer system. Significant amounts of the conjugate base and its weak acid, or vice versa. We could also use a weak base and its conjugate acid. And so buffers do not significantly change. They minimize pH changes in the presence of added acid or base. Now, it is very possible to overwhelm the buffer. So what we say is that the buffers have a certain capacity, and it usually is related to the amount of added acid or base. That can be absorbed by the buffer. And it depends on where you are in the acid and base and how much of the conjugate acid and how much of the conjugate base. So usually the best buffers are a mixture of somewhere between 10 to 1 acid to base, or 1 to 10 acid to base. So if you're trying to soak up a lot of acid, you probably want a greater amount of the conjugate base. What this does is sort of fixes the Ka, fixes a pH range around the Ka of the weak acid. and some will sort of float about 1 pH unit around the weak acid. So one of the things we have to be aware of is that there are 2 ways to create a buffer. You go to your shelf and you grab some acetic acid, and you grab yourself some salt of that weak acid, sodium acetate, which turns out to be a weak base. Again, a weak base that is the conjugate base of this acid. Remember all that time we spent figuring out which is a conjugate acid, which is a conjugate base. This is where it pays off. And then you mix them. And we can then treat them with our weak acid assumptions, or what we're going to talk about in a second or two, we'll use something called the Henderson-Hasselbalch Equation, which will greatly simplify our lives. Now, the alternate way to make a buffer, and one of the more common ones in the lab, is you take a solution that contains some sort of weak acid or weak base. Sometimes you pop a pH probe into it, and then you start adding base, such as a strong base like sodium hydroxide. And then you add the sodium hydroxide until you reach the pH appropriate for the system. Now, what this does is as you add that sodium hydroxide, all of that weak acid starts to react. As you start this reaction, the system consists almost solely of our weak acid. And then you start adding base, which then converts that into our conjugate base, allowing us to build up an amount of weak base present in solution. So we create the weak base in situ within the system. Another common way. So this is, again, one of the more common ways to do it in the lab. Again, the pH of these systems sort of is very much tied to the pKa of our weak acids. So if you remember, I've passed out a table of pKa in the lab, and the reason I did this is because that we can use that in our problems, but we can also use it in to find an appropriate pH range. So if we wanted a pH of 6 with a pKa between 4 and 7. Now, as I was saying, buffers are incredibly common. So common that it's possible to modify the Ka statement into a simpler form, incorporating the assumptions that we've already talked about. And this is what we call the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is as follows. I'm not going to derive it. All right, you go online. There's this lovely thing called YouTube or the internet or something along those lines, where you can type stuff in and it will show you vast amounts of information. Some of it is even correct. And you can find the derivation of the Henderson-Hasselbalch equation. It's relatively trivial, but it's cool to watch. Why is it cool to watch? Because one of my favorite test questions, flashing sign that says subtle hint, all right? One of my favorite test questions is, derive me a form of the Henderson-Hasselbalch equation that relates POH to pKa. The Henderson-Hasselbalch equation relates pH and pKa of these two quantities, and the form of it is this. The pH of a given system will be equal to the pKa of the conjugate acid plus the log of the conjugate base, which I'm just going to label as base, over the conjugate acid. Things to remember: that this is the conjugate base and this is the weak acid. And this is the pKa of the conjugate acid, of the weak acid. So, Henderson-Hasselbalch equation. Something you should probably memorize. It's well worth your time. pH is equal to pKa plus the log of the base over the acid. And this would be for a generic weak acid. And this works under dilute conditions, because of the assumption where the amount of the conjugate base and the amount of the conjugate acid are relatively unchanged as the reaction progresses. What's nice is that because it relates to the ratio of the base to the acid, we can often use moles rather than molarity for these, even though they're listed as concentrations. We can often use moles rather than molarity because they are a ratio. The units would drop out. And that's a very big time saver for us because, as we talked about last, it's very easy to find the number of moles of conjugate base or number of moles of conjugate acid. Additionally, because this is a ratio, buffers are great because you can dilute them without radically changing the pH. Normally, again, with an acid or a base on their own, when you dilute them, well, that's by default changing the hydronium ion concentration. pH buffers, on the other hand, are not as easily perturbed when you dilute them. Another good feature. Though it does change the buffer capacity in some respects. So just keep that in mind. And because of this ratio and the log function of this ratio, again, a 10-to-1 ratio of acid to base means about a 1 pKa units. So effective buffers usually have a range of about no more than 2 pKa units, 2 pH units. After that, you start to get too much base or too much acid, and makes the use of this equation less reliable. All right, so let's put it into action. Let's take a look at a typical problem. What is the pH of a solution made by mixing 33 mils of a 0.1 molar sodium nitrite with 45 mils of a 0.2 molar nitrous acid solution? Again, like, we can tell that this is a buffer problem because, again, we have the weak acid and a weak base. So we can go to our tables and we see that, well, first we do, look at the problem. Look, this is a weak acid. So we can identify this as the weak acid, and we can look at this and say, oh, the weak acid, this has a Ka, we go to nitrous acid on the table, we can see that the Ka for this is equal to 5.6 times 10 to the negative fourth. And then using whichever method you so dearly like, you can convert this into the pKa, which is the negative log of the Ka, be equal to pKa is equal to 3.251.52. And once we have that number, we can then use skills from last semester to convert this into the moles of our weak base and our moles of our weak acid. Now, you could do it the long way. You can say, okay, we have this solution, we could do a dilution, and then we can then say how much is actually left. But combining these, it's just really long, drawn out. It's correct, but it's a waste of your time because these solutions are poured together. They all have the same volume. The number of moles doesn't change. We can use the number of moles of the weak acid, the number of moles of the weak base, and plug them right into our Henderson-Hasselbalch equation. So we can find our mole volume and our molarity together, give us the moles. So this is a 3.3 times 10 to the minus third moles of sodium nitrite, 9 times 10 to the minus third moles of our weak acid, nitrous acid, and we have our pKa. We can then use our Henderson-Hasselbalch equation, which says that the pH of that solution will be equal to the pKa plus the log of the base divided by the acid. And so the pH will equal pKa 3.252 plus the log of the base, 3.3 times 10 to the minus third moles divided by 9 times 10 to the minus third moles to give us this ratio is 0.366. The log of that number will equal 0.4357 negative. So this would become 3.252 minus 0.435, or 2.816 as the new pH. So very typical problem. Start with the number of moles of acid you have, start with the number of moles of base, solve for pH. Alternately, you could be given a target pH and you'd have to find the ratio. Let me look at probably one of those examples in class. Now notice, this number is more acidic compared to the Ka. The Ka is 3.25, this one is lower, meaning more acidic, which makes sense. We have more acid present. The number of moles of acid is greater, which gives us a big thumbs up.